being kind sometimes means to tell the inconvenient truth. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. Asleep or not, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. The inconvenient truth? Well, physics is crazy. Period. It just is. And that's okay. We can say it out loud. Actually, it's awesome. Listen to that piece about me not being a genius. I love physics because it's crazy. That's crazy. For example, we are quite literally stardust. That's inspirational, right? It's one of the, let's say it's an idea which arises out of the way stars form, radiate their light, and eventually disappear. What they call the life cycle of stars, quote unquote. Part of it all, an important part too, is what's called nucleosynthesis, or the creation of new atomic nuclei in the stars. Now, in order to fuse atoms into other heavier ones, you need temperatures which are higher than we can imagine. The process only happens under extreme circumstances. In the Sun, we get hydrogen fusing into helium. If the star is heavier, say around 8 to 10 times heavier than the Sun, elements such as oxygen, neon and magnesium can be created too. We're talking reactions that require several hundreds of millions of degrees. It doesn't matter anymore whether it's Celsius or Fahrenheit or whatever. In science we use Kelvin. That's Celsius, but actually starting in zero, not at minus 271 point something. There's also silicon fusion. Silicon and sulfur turn into iron, though by means that are a little different and involve hundreds of different reactions, thus creating all the other elements up to iron as well. So we have solar fusion, we have heavier star fusion, we have silicon fusion, which also happens in heavier stars. We get iron itself and all elements lighter than it out of these reactions. Okay, but you may point out that iron is not the heaviest chemical element we know of. What now? Think about it like this. Fusion reactions are one of our attempts to create on Earth the energy source of the stars. It takes a lot of energy to start a fusion reaction, but once it has started, it releases energy. That's been true for all fusion reactions mentioned before. It's what makes the sun shine, as close to literally as it gets. But from iron and onto heavier elements, it'll take energy to start the fusion, and it'll keep costing you as the reaction continues. Thus, the core of heavier and older stars is made of iron. But that's the thing. Once iron assembles in the core of such a heavy star, the radiation outwards becomes less and less, and that's not really a good thing for the star. Well, good and good. It's bringing it nearer the end of its existence, to put it like that. Well, no, that's not true either. It rather kind of changes in a way that reminds science communicators of death. Anyway, what I'm saying is, gravity doesn't disappear. Radiation pressure does. The star implodes first, then explodes into a supernova. And there you'll get the conditions just right to create even heavier stuff than iron. Well, there, and in what's called shell burning. There's also something called the asymptotic giant branch in star classification, but I can't even. Read for yourself if you must, and as I have done, because it's cool stuff, but be careful. Once you dive deeper into it, you'll find sentences like, stars are factories whose main business, quote unquote, is either this or that. Stars have a life cycle, quote unquote, after all. They're living things with a purpose, and sometimes it seems a consciousness even. If I was allowed to call it my job to study stars, I'd talk about them like that too, so it's not that. It's just, be careful dipping into this subject, okay? Besides, trash cans and the trash inside them are stardust too. Of course they are. We've got more hydrogen in us than metal or plastic trash cans do, and hydrogen is not created in stars, so perhaps they are stardust even more than we. That's crazy. I mean, think of science and history. How did science come about? Whenever we think of putting a number like, for instance, for 6,000 years, quote-unquote, onto the history of science, we need to remember, as it were, the circumstances in which whatever science was back then existed. Who had access to those star charts, for example, which we cite as proof for astronomy being such an old discipline? It was exclusive knowledge, and it was treated as such. It filtered down to the common man, if at all, via a high priest or someone who could very well be a sort of high priest, like a pharaoh in Egypt whose kingship incorporated parts of a high priest's role. We're talking religion and, in fact, power plays. Sorry, there's no way around putting it like that either. Still, with time, measurements were made and discussed. Within the Western world, the Hellenics started doing that. What is a unit of length? Find an answer and off we go. In India, Arabia and China, people were doing stuff like this before, but what separated the Hellenics was how they treated the knowledge they acquired. No kings involved, basically, mostly. They got the ball rolling, underline. See, what these discussions eventually led to was physics, that is, the attempt to describe nature by means of mathematical equations. Kepler, Newton, and all their contemporaries. What did they really do if not put formulas into everything they knew? Planetary motion, falling apples, and everything else. A mechanical universe, quote-unquote, as Newton saw it. That's the thing with us people, though. It's not enough to know how that apple falls onto our head, or even just realizing why the moon doesn't. No, we have to push further. We have to see where our limits are. And whether you like math yourself or not, it's a powerful tool for that kind of push. In other words, using it to explore increasingly abstract concepts in nature was only a natural thing to do. And thus we have general relativity and quantum physics. General relativity, by the way, is a system of 16 hyperbolic elliptic partial differential equations that we cannot solve, like at all. We use a sort of street fighting mathematics on it. We do that with everything else in modern physics too. We have to. It's the sort of thing pure mathematicians hate. One of them, a friend of mine, puts it like this, and I quote, "Physicists mug mathematics," quote end. Not that I disagree. We wrestle knowledge out of nature. How surprising is it really that we don't understand that stuff anymore? Planck length or galaxy cluster movement. You tell me that you understand it and I call you a liar. Well, no, not directly, but I will imply it strongly. You know, kindness through knowledge and inconvenient truths and all that. What did you say? The idea of mugging equations was kind of funny? Maybe. To me, it's just crazy. It's crazy, but it worked often enough. With quantum physics, we even needed to do it in order to explain what we saw in observations and experiments. At university, you may very well be introduced to the respective subject by means of the Stern-Gerlach experiment. And then you will be asked to skip asking why what happens, but ask yourself what the consequences of that electron beam splitting up in that magnetic field would be. 8 years later, you may call yourself a doctorate in physics, and you still won't have understood exactly why that experiment made electron spin visible. Here's what the book says, and I paraphrase. "See, it's the spin, and the spin is..." Insert long explanation here. "And it all comes quite neatly out of the Lorentz transformations which we find in nature." Insert another long explanation here, and I'll stop. Because you could start with observations in nature instead of an observation of a controlled experiment, yes, but that doesn't change things now, does it? In that case, too, you ask the question of consequence, not of cause. In other words, you build your theory on nothing. You can simply state that it works, and work it does. Without it, modern life is a pipe dream. All of it. And you have a choice. Either you find this thought scintillating, or you're afraid. Or maybe there's a little bit of both in you. It's awesome for sure, and hopefully if you're a modern scientist it makes you look upon those medieval architects just a tad less haughty. Because you're used to your equations, aren't you? Like they were to their keystones. Nobody else is though, and well, to be honest, to everyone but you it's just one big chunk of WTF. I mean, to be fair, when calculating stuff, most terms in whatever equation you think about now will not be relevant and you're left with mostly 2 or 3 terms. Maybe sometimes a few more than that. Then again, most of those letters on your paper are so-called tenses, not just numbers. For those who don't know, there's a link down there in the description to what a tensor is. The link tells you what a tensor is. I'll tell you what these letters being tensors means. Even just 2 terms being left may lead to a system of equations you will have to wrestle to the ground like an angry badger. That's what that means. The equations are the badger in that simile, not you. You wrestle the... never mind. At any rate, your best weapons against that badger are symmetries. Symmetries are the stuff that doesn't change during the transformation of a physical system. Well, something happens, and symmetry is what doesn't change during whatever happens. We love symmetries because they mean that we can set something to 0 and take it from there. The total energy is one of those in school physics. The total energy of a system doesn't change. We set its change in time to 0. The universe itself works like this too. It's got a total energy. If that total energy turned out to not be constant over time, then that would be something to ponder for sure. Multiverse and whatnot. To be honest, that's crazy. It would be extraordinary to find out that the universe's total energy isn't constant with time. Actually, I don't know whether we don't know. It's not important to the bigger point of this piece either. Because you know us, we don't stop pushing onwards because of stuff like this. Heard of string theory? If you followed me wherever you listen to or watch this, you certainly have. I won't repeat what it is, just know that people who are good at street fighting mathematics use their street fighting mathematics to make equations bend to their will and give us one or more theories of everything. Only nothing about these theories, quote unquote, can be tested. So there's that. They're not theories, but that's a, different story. Others claim to have found references to an earlier universe in what's called cosmic background radiation. The way we look at it now, both space and time began at the Big Bang. Both time and space are intrinsic parts of our universe. Think of the 3 dimensions. Time belongs to the universe in the same way. How can anything be earlier then? Any other universe would have its own time. Now, I'm not going to be like Ernst Mach, who didn't believe in atoms because he couldn't see or touch them, so who knows, and this is indubitably true, as of today, these ideas are exotic, to say the least. Talking to string theorists and multiverse people, I get the hunch that they know this very well too. But there's also the enthusiasm that comes with taking an idea and running with it much too far. At the very least, the motivation for it radiates out from the right place, so I'm not even mad at anybody. And if those guys can get their research financed, then good for them, I say. To be honest, I'd love to be wrong about what they do too, even though there was one person telling me that nobody, quote-unquote, believes that when I say it. Anyway, we don't have to go into all the fancy schmancy stuff. Think about a square. That's a 2-dimensional geometric object with 4 corners and equally long edges. Now enter the 3rd dimension and you get 8 corners and a few more edges, but you still know exactly what it's going to be, a cube. Now enter the 4th dimension, only you can't, and still we can give the geometric object a name. Tesseract or hypercube. We can calculate everything about it too. But do you know what it looks like? Tell me yes, and I'll call you a liar. Well, no, but I'll strongly imply it. Kindness through knowledge and inconvenient truths and all that. And most of all, that's geometry, not physics, right? wrong. Well, no, it isn't really, but yes, it kinda is. Hear me out. In the 1800s, there was a Swiss polymath called Leonhard Euler who thought it would be a neat idea to express systems of equations in the form of matrices. Along came the physicists of the early 1900s and realized how nice this idea was and how it could be used to note down what is called tensors. There's that word again. You could express long-winded equations easily and, well, beautifully. A couple of letters here and there, that's it. Hide all that nasty badger fighting stuff, right? We like things that are beautiful, don't we? So we explored what we could do with this shiny tool. Modern physics, that's what we could do. There is a case to be made that without matrix calculations we would not have general relativity or quantum physics. Why? Because the tool in this case gave us a way to deal with all the stuff that cannot be imagined. You know, like we're in a dark room, we don't know how the cake was made or how it even looks, but we stumble into it. Well, not into it, because then we couldn't. Well, anyway, we found the cake and started eating it. Because we could. Think about it. That's crazy. The worst thing about all of this is that we shy away from teaching the craziness properly in school. We need to do it. It's fundamental to dealing with the world around us. And to boot, I just think that the craziness of it all is awesome and not torture to learn about. I also know that I'm not alone in thinking that. I mean, have you ever looked through an oddly shaped piece of glass? We've all done that in school at least. We looked through prisms there, didn't we? And we said, cool, at the colors and moved on. Colors. Think about colors. Most of them you can't see, but our instruments can. In fact, we can receive light with our instruments and split it up into its colors. There are no jumps in the spectrum of colors either. The difference between blue and red is what our brain does to the whole thing. Nature doesn't think like that, and why should she? The colors are all there, pretty much per definition, and we can see them all with the help of eyes and instruments. The key word is spectroscopy. Without it, we wouldn't know the universe. See, it turns out that different chemical elements react to light in different ways. In fact, they react in rather distinct ways, such that we can use light to distinguish the elements from each other. For example, when looking at sunlight with the help of spectrometers, we find that yes, it's white light, but also that there are a few colors which we see less of than expected. Combine this with other measurements and realize that some of those colors get absorbed by the chemical elements in the air, in our own atmosphere. Thus, we can learn about the Earth's atmosphere like that. The kicker with that sort of thing is that it works just as well when we put that spectrometer at the end of a telescope and point it at a distant star. Stars do that sort of thing to their own light too, or they may even create a particular color en masse, and we see that in the spectrum. And all these colors are connected to certain elements, such that we can estimate there to be 74% hydrogen, 24% helium, 1% oxygen, 0.5% carbon, and a little bit more than 0.1% neon in the Milky Way. Yeah, we know this due to colors and the way we look at them. If you're wondering, we can't estimate these percentages for the whole universe for quite a few reasons, but mainly because we don't know how big that universe of ours really is. Anyway, here we sit inside of the Milky Way, telling ourselves that it is a barred spiral galaxy of 100,000 to 120,000 light years in diameter and consisting of 400 billion stars. Okay, that last one is a matter of counting, you may say. Please do count to 400 billion. I'll wait, or wait, I won't, because you won't get there before you die. I'll live my life while you follow your passion, if that's quite okay for you. And that first one? How can we know what the Milky Way looks from the outside while sitting inside? I mean, that's crazy. How do we know that the Milky Way is a barred spiral galaxy of 100,000 to 120,000 light-years in diameter and consisting of 400 billion stars? Let's start with that last claim. To count the number of stars in the night sky that are visible to the naked eye, you will use a small cardboard tube. The center tube of a roll of toilet paper is ideal. On a clear, dark, moonless night, hold the tube up to your eye, then count and record the number of stars that you can see through the tube. That's a quote from a page I'll link to below. The professional version isn't that different. Most super telescopes have a rather narrow field of view, quote unquote. Make it even more narrow artificially and follow the process. Then scale that up to whatever piece of sky you're interested in. Such, we know how many stars there are in the Milky Way. We can also track the movements of stars by spectroscopy and colors, and how they are shifted away from what we would expect. Then we do geometry in our heads, or on pieces of paper, or with the help of supercomputers, and conclude after a while that we live inside a so-called barred spiral galaxy. Aren't we the clever species, huh? To interject quickly, the history itself is a little bit more complicated than that, and involves realizing that there was such a thing as a galaxy in the first place. For most of science history, we considered the Milky Way to be the universe, period. In terms of school physics, this is, of course I might add, not really easy to discuss. Sure, we can repeat all the talking points from TV, all that big banging and universe expanding told in front of either a starlight or a sunlight shot. I won't though, I just want to appreciate for a second just how intriguing these things are to especially kids, and how difficult it is to talk about them properly, that is, without dumbing down and still communicating its awesomeness. We guess sophisticatedly about nature, and have the endurance and interest to follow any old weird line of thought. We have historically been awesome at following any old weird line of thought. That's it. Being kind sometimes means to tell the inconvenient truth, because that's it. Nature's complex, so it takes thousands of weird ideas to get to that one idea which works. But science isn't complex. Science is just coming up with those weird ideas. Well, within boundaries, of course. You can ask questions and take a guess. But if you don't know how you would check whether you're right, then you can just forget it. That's the only limit though. The only limit. Just take energy. The total energy is the stereotypical example of a symmetry. It doesn't change, never does in a physical system, yet you don't know what it is, even though you may think that you do know what it is. You really don't, because you can't. It's like flying. You simply can't unless you use a plane or some such contraption. Energy is nothing you can understand unless you use math or experiments or some such thing to gain experience with it. Physicists do just that. Mostly they do just that and get all giddy when a proposed symmetry is broken, that is, it's not holding. That in itself is crazy too, and you know that's okay. Physics is crazy. It's a discipline that hops from one thing to the other incrementally, but still in ways that are impossible to predict. It has to be like that too. It is, after all, the science of stuff we have no right to know. In fact, one may argue that it is the science of stuff we are not even in a position to really ever know. I mean, honestly, what is gravitation, for example? It's a theory, okay? It's got to do with stuff falling down, but what is it? What makes stuff fall down? I don't know. Do you? And isn't it crazy that we don't? Thanks for staying with me to the end. Join me on socials and YouTube, or check out kindnessthrough knowledge.com to book a presentation. See you next time.